true projects. In this video, we are going to explain about toward detection and attribution of cyber attacks in IoT-enabled cyber-physical systems. Introduction. The project addresses the integration of Internet of Things IoT devices with cyber-physical systems CPS with a focus on critical infrastructure sectors such as dams and water plants. These IoT devices are frequently part of an industrial control system ICS, which is in charge of ensuring the infrastructure's reliability. However, connecting ICS or IIoT based systems to public networks expand their attack surfaces and increases the vulnerability to cyber criminals. The project emphasizes the significance of developing exceptionally robust safety and security measures to identify and prevent ICS attacks. The project also addresses other approaches to attack detection and attribution, such as those based on signatures and anomalies, hybrid approaches in machine learning or deep neural networks. Objective. The project's objective is to present a novel two-stage ensemble deep learning-based assault detection and attribution methodology for imbalanced ICS datasets. The proposed framework intends to solve the constraints of existing techniques that describe just a system's normal behavior and report deviations from normal behavior as anomalies, ignoring the imbalanced feature of ICS data. Using machine learning techniques, notably deep neural networks, the system is intended to detect and attribute attacks on ICS datasets. The suggested method should increase the accuracy and efficiency of attack detection and attribution in ICS datasets. Requirements. The requirements of the project are hardware requirements and software requirements. In hardware requirements, we have operating system Windows only, processor i5 and above, RAM 4 GB and above, hard disk 20 GB and above. Software requirements. In software requirements, we have Python IDEL with 3.7 version. Methodology. To implement this project, we have designed the following modules. The first module is Upload SWAT Water Dataset. Collect a dataset related to the SWAT, Soil and Water Assessment Tool framework, which is often used for water resource management and hydrology modeling. This dataset includes data on soil properties, climate, land use, and other relevant factors. Second module is Pre-process Dataset. Prepare the SWAT water dataset for further analysis. Steps might include data cleaning, handling missing values, scaling features, and encoding categorical variables. The dataset should be structured in a way that's suitable for training and evaluating machine learning models. Third module is Run Autoencoder Algorithm. An autoencoder is a neural network architecture used for feature learning and dimensionality reduction. It's trained to reconstruct its input data and has a bottleneck layer that represents a compressed version of the data. In this context, we use autoencoder to extract meaningful features from the SWOT water dataset, potentially highlighting patterns relevant to cyber attack detection. Fourth module is Run Decision Tree with PCA. Principal Component Analysis. PCA is a dimensionality reduction technique that transforms data into a new coordinate system. Applying PCA before using a decision tree model can help mitigate the curse of dimensionality and improve the model's efficiency and generalization. The decision tree classifier could be trained on the PCA transformed features to identify anomalous patterns indicative of cyber attacks. Fifth module is Run DNN Algorithm. A deep neural network DNN is a type of neural network with multiple hidden layers. In this module, we design and train a DNN to learn complex relationships between the features extracted from the SWOT water dataset and the occurrence of cyber attacks. DNN are well suited for capturing intricate patterns in data. Sixth module is Detection and Attribute Attack Type. After training the models, we use them to detect and attribute cyber attacks in IoT-enabled cyber-physical systems. Detection involves identifying instances where the system's behavior deviates from expected norms, indicating a potential attack. Attribution involves determining the type or source of the attack. The models might provide predictions or confidence scores regarding the attack's presence and characteristics. Seventh module is Comparison Graph. Create a graph that compares the performance of the different models we have trained. This graph depicts metrics such as accuracy, precision, recall, FN score, or area under the receiver operating characteristics curve. The graph helps us to access which model performs best and under what conditions. Execution. For the execution of the project, we need to open the code folder. This is the code folder. This is the dataset folder. To implement this project, we have used SWOT dataset. SWOT, Secure Water Treatment. contains IoT request and response signature and associate each dataset with unique attack label, and dataset contains below cyber attack labels: normal, navy malicious response injection NMRI, complex malicious response injection CMRI, malicious state command injection MSCI, malicious parameter command injection MPCI, malicious function code injection MFCI, denial of service DOS. In above dataset screen, first row contains dataset column names and remaining rows contain dataset values. And in last column, we have attack type from label 0 to 7. We will use the above dataset to train proposed autoencoder, decision tree, and DNN algorithms. This is the test data. New test data which contains only signature and there is no class label, and proposed algorithm will detect and attribute class labels. In above test data, we have IoT request signature without class labels. This is the model folder. This folder contains pickle and .h files stored, which contains algorithm information. These pickle and .h files can be loaded into the project code during runtime to utilize the train models. This is the main code file. This is run.batch file. Instead of executing our project in the command line interface, we have created Windows batch file to execute the project. Double click on run.batch file. This is the graphical user interface which we have created using Tkinter library in Python. Using this GUI, we will interact with the project. Click on upload SWOT water dataset to upload the dataset. Select SWOT dataset and open. So here we can see that the dataset is loaded. So the dataset is loaded and these are the values present in the dataset. And here we have command address, response address, command memory, etc. And this is the graph. Various cyber attacks found in dataset. X-axis represents the cyber attacks and Y-axis represents the value of the attack. So from this graph, we can say that normal cyber attack is having the highest value compared to the other attacks. Now close the graph. Click on pre-process dataset to process the dataset. So here we can see that the dataset is processed and we can find the total records found in dataset and total features found in dataset. And the dataset is split into training and testing, where training is of 80% and testing is of 20%. Now click on run autoencoder algorithm to get its accuracy. After training autoencoder algorithm, we will get the accuracy, precision, recall, F-score of autoencoder. Now click on run decision tree with PCA to get its accuracy. After training decision tree with PCA, we will get its accuracy, precision, recall, and F-score. Now click on run DNN algorithm to get its accuracy. After training DNN algorithm, we will get its accuracy, precision, recall, and F-score. Now click on detection and attribute attack type. Select the test data and open. So here we can see the test. This is the test data. And this test data is detected as no cyber attack detected. And this test data is detected as cyber attack detected. And here we can find the attribution level and as well as denial of service. In this way, we can predict which test data is cyber attack and which test data is not cyber attack. Now click on comparison graph. So this is the comparison graph. X-axis represents the different types of algorithm and Y-axis represents the values of accuracy, F-score, precision, and recall. And each algorithm is having different metrics and each metric is represented with a different color. So here we can see that accuracy is represented with blue color, F-score is represented with orange color, precision is represented with green, recall with red. So here we can see that from this graph, we can say that DNN algorithm performed well. Now close the graph. Click on comparison table. So this is the comparison table. So here we are having the algorithm name, accuracy, precision, recall, and F-score. From this table, we can conclude that DNN performed well. Now close the table. And the final conclusion of the project is the proposed two-stage ensemble deep learning based attack detection and attack attribution methodology is effective in identifying and attributing assaults on imbalanced ICS datasets. According to the project's finding, the attack detection stage maps the samples to a new higher dimensional space using deep representation learning and detects the attack samples using a decision tree. The attack attribution stage is made up of numerous one versus all classifiers, each of which has been trained on a different attack attribute. The model as a whole builds a complicated DNN with partially and completely connected components that can appropriately contribute cyber attacks. Despite the proposed framework's complicated architecture, the computational complexity of the training and testing phases is comparable to that of existing DNN-based techniques in the literature.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.